Let's start with private versus public IP. Private addresses are used internally and are normally protected by a firewall. They do not have a direct connection to the internet. A couple common examples include 192.168.1.1 or 10.0.0.1, which you've seen before. However, public addresses are addresses that are displayed directly to the internet. And a public address can be just about anything except for the private ranges. Those private ranges are assigned by the IANA for internal use, and there are particular ranges reserved for Class A, B, and C. Class A has the 10 network reserved for internal use. Class B has 172.16 all the way through 172.31 reserved. And Class C is 192.168.0 all the way through 192.168.255. A couple examples of this: D-Link uses the 192.168.0 network by default. Linksys uses 192.168.1, and Belkin sometimes uses 192.168.2. So some examples of internal Class C networks. There's also something known as a Pipa, automatic private IP addressing, which is used on Microsoft machines but not assigned by the IANA. And if you see an address that starts with the network number 169.254, you know it's a Pipa. Sometimes a Pipa can get to be a nuisance and it could get in the way. In Lab 5, Configuring DHCP, I'll show you how to disable a Pipa. This documentation shows some more examples of private and public IPs. On the lower left-hand side, we see the Class A10 network. We know that's an internal private IP network. On the other side, on the upper right, past the internet, we see two servers. One of them is 208.96.234.193. That's an actual IP address of a server on the internet, and that's a public IP. And it would have to be public. It needs to be publicly displayed to the internet so that people can see the contents of that web server. To further show public and private IP addresses, we can run an ipconfig/all in the command line. And you'll see the IP address 172.30.250.3. That is a private, internal, reserved network, 172.30. But also you'll notice the DNS servers. They're on the 208.59.247 network, and that is public. Also, we could use the ping command to show this a little bit more. For example, we could do a ping to Microsoft.com. When we do so, it pings Microsoft.com and resolves that to its public IP, 207.46.232.182. Another example, ping davidlprouse.com, and that'll resolve to its publicly assigned IP address. Or we could ping CompTIA.org or CompTIA, whatever we're calling it nowadays, and that'll resolve to its IP, the one we saw before on our network documentation, 208.96.234.193. Next is network address translation. NAT, or network address translation, is the process of remapping one IP address space to another. And NAT is commonly used to hide a private network address space behind a single public IP address, otherwise known as IP masquerading. Here's an example. The multifunction device here has two IP addresses. On the LAN side, it has the 10.0.0.1 address. That's considered the private address. And on the WAN side, it has the 207.172.15.50 address. And what this device does is it translates for all the computers on the 10 network, but displays all their outgoing requests to the internet with that one publicly displayed address of 207.172.15.50. Let's show an example of this on our Belkin router. I'm going to go to my browser and we'll connect to the router by typing the IP address. And right on the main page, we see a lot of information, including LAN settings and internet settings. The LAN settings tell us the local IP, or the internal or private IP that we're using for this device, which is 172.30.250.1, the address I used to connect in the browser. But on the WAN side, it shows us the address that's being assigned to us by our ISP. That's the WAN IP, or the public IP, 216.164.158.43. So this device translates all the data coming from the private side into one IP address. It converts from the private IPs to the one public IP. Alright, moving along, before we delve into subnetting, let's do some subnet mask review, namely default subnet masks. The Class A default is 255.0.0.0, and this tells us that the first octet of the IP address is the network portion, and the other three octets are the node or host portion. This is suitable for very large networks with a lot of computers. In binary, there would be 8 ones and 24 zeros. Class B default is 255.255.0.0. So the first two octets deal with the network portion, and the last two deal with the node portion. In binary, we have 16 ones and 16 zeros. And Class C, 255.0, the first three octets deal with the network portion, and the last octet deals with the node or host portion. And in binary, we have 24 ones and 8 zeros, and this is suitable for small networks with a small amount of computers. Now let's talk subnetting. What is subnetting? Subnetting is the act of dividing a network into smaller logical subnetworks. Now let's show an example of a subnetted network address. The IP network 192.168.1.0, which normally would have a subnet mask of 255.255.255.0. But when we subnet, we're going to use 255.240. What we're going to do is we're going to borrow bits from the host portion. This could also be represented as 192.168.1.0/28 because there's 28 ones in the subnet mask in binary. Let's talk about the golden rules or equations I like to use. Equation 1, 2 to the n power equals x. With this equation, you can find out how many subnets are possible on the network in question. And equation 2, 2 to the n power minus 2 equals x. With this rule, you can figure out how many available hosts there are per subnet. Let's show an example of this. The subnet mask 255.255.255.240. What you want to do is you want to take 240 and convert it to binary. That becomes 11110000. Now, the masked bits, or ones, tell us how many subnets we can have. There are 4 ones in the binary number 11110000. And what we do is we plug that number into our equation number 1, which was 2 to the n power equals x. That becomes 2 to the 4th power, because there's 4 ones in that binary number, equals x. So 2 to the 4th power equals 16. So there's 16 usable subnets in this particular example. We've subdivided our network into 16 usable subnetworks. Now the unmasked bits, or the zeros, tell us how many hosts per subnet we can have. There are 4 zeros in the binary number 11110000. So now we plug that into our equation number 2. 2 to the n power minus 2 equals x. So it's 2 to the 4th power minus 2 equals x. And again, 2 to the 4th power is 16. Minus 2 equals 14. So we can have 14 usable hosts per subnet in this particular example. And that's because we can't use the first or the last. The first is dedicated to the subnet ID, much like a network ID. And the last is for the subnet broadcast address. Here's the entire table of IPs within 22255.240. And this may seem like a lot of information at first, but if you look at the left-hand column, we see the subnets, which are just being shown in binary and in decimal. So the ID numbers go from 0 to 15. For each of those subnet IDs, we can have hosts between 0 and 15. The usable hosts are going to be a little bit less than that though, because we can't use the first and we can't use the last. So for example, in subnet ID number 1, we have the host IP range of 16 to 31, but we can't use 16 because that's the subnet ID number, and we can't use 31 because that's the broadcast. So our usable range is 17 to 30. For subnet ID 2, the usable range would be 33 to 46, and so on. Let's go ahead now and subnet the network. We're going to use the network number 192.168.50.0 and the subnet mask we just showed before, 255.255.255.240, otherwise known as 192.168.50.0/28. The subnet ID I want to use is 8. So the subnet range is 128 to 143, and the usable IPs in that range is 129 to 142. So I'm going to assign the server the 129 address and the laptop the 130 address. Let's show that now. First, I want to reconfigure the IP address of the server so it can join the subnet. And by the way, when I'm making connections to the server, I usually use an RDP connection, or remote desktop protocol. Now, we said that making modifications to IP addresses on the server is the same as on a Windows client. So we'll go to the IP properties window, and we'll go to the IP address field and plug in the correct address, 192.168.50.129. The subnet mask is 255.255.255.240, and I'm not really interested in a default gateway at this point. By the way, this server does a lot of things. It's a domain controller, it's a DNS server, and since it is a DNS server, I'm going to put in its own IP address for a preferred DNS. We'll click OK and close to bind that information. And now we need to go to the laptop to make changes to the local area connection here. So we'll do that now. And we'll change the IP address, 192.168.50.130. Subnet mask is once again 255.255.255.240. And not really interested in a gateway or a DNS address. All we need to make this lab work is the IP address and subnet mask. Click OK and close that to bind it. And once again, we want to test. Be sure to test whenever you do any configuration. So we can use the ping command to connect to the server. We'll go to the command line, and first I'll run an ipconfig and just take a look at that IP address and that subnet mask. Looks good to me. You never know if it bound or not when you closed that last window, so a quick ipconfig can check that for you. And then we want to run a ping to the server, 192.168.50.129, and the magic replies have arrived. I can connect to any computer on this subnet. However, if I try to connect to computers on other subnets on the 192.168.50 network, I should not be able to do so by default without a routed connection. So for example, let's say I wanted to ping a host on subnet ID 2. Well, for example, that would be ping 192.168.50.33. It says destination host unreachable because it's on a different subnet from me. And that's the beauty of subnetting. Subnetting creates a wall between the various subnets. It makes a more secure network, and it reduces the amount of bandwidth that's being used. As you can see in this diagram, I have two subnets. Subnet ID 8, where my laptop exists, .130, and subnet ID 2, that other host I was trying to ping, .33, which by the way does exist on this network, but I wasn't able to ping it because it's on a different subnet. A computer can ping hosts on its own subnet, but by default cannot ping hosts on another subnet. And that's part of the whole reason of having subnetting. It compartmentalizes your network. It also increases security and reduces the amount of bandwidth that's being used. It reduces broadcast traffic. Now, it may become a little bit tough to work with the math in subnetting, So there are several good subnetting calculators on the internet, and I do use them. Now, you can't use these on the exam, and in lieu of that, I've added some subnetting tables to the cheat sheet in the back of the lab booklet that accompanies this product. Let's talk CIDR. CIDR, or classless interdomain routing, was developed to allocate IP addresses more efficiently and was based on VLSM, or variable length subnet masking. Many network people use this term synonymously with supernetting, but really CIDR is a combination of supernetting and subnetting and just regular old netting. An example of CIDR would be 192.168.0.0/16. The /16 tells us we have a subnet mask of 255.255.0.0. Well, usually if you see 192.168, you're thinking Class C, triple 255 subnet mask. But that /16 tells us we're using a Class B subnet mask for a Class C address. So what would typically be considered a Class C network with a maximum of 254 hosts is now a classless network with up to 65,534 possible hosts. Okay, in this lab we covered private versus public IP addresses, the assigned private IP ranges like Class A 10, Class B 172.16 through 172.31, and Class C 192.168.x. We talked about NAT, or network address translation, and we showed you how to configure subnetworks. Plus we went over a brief description of classless interdomain routing, or CIDR. By the way, DHCP is another concept related to this lab, and for more on DHCP, see Lab 5, Configuring DHCP. Up next is Lab 3, Protocols and Ports.